All right, in this video, I'm going to go over section 6.4. Okay, so central limit theorems. So let me go over that section using my lecture handout. So 6.4 is talking about um, 6.4 introduces central limit theorems. So now, what's central limit theorem? Look at this. Select the random samples of size n from a population with a mean mu and standard deviation sigma. If the population normally distributed, then for any sample size n, the sample mean x bar is normally distributed with the mean sigma mu x bar is equals mu, and standard deviation sigma x bar is sigma over square root n. So that means that's the first statement of central limit theorems, and then that statement says that if the population is normally distributed, then the mean of sample mean. Okay, so mu x bar denote the mean of sample mean. Remember that in 6.3, we the we select the many samples, and then we calculate the mean sample means for each samples, and then the sampling distribution of the sample mean is normally distributed, so that the mean of sample means target the value of population mean, right? So we learned about this one in 6.3. So central limit theorem is kind of the conclusion of the uh, the research in 6.3. So the the mean of sampling distribution denoted by mu x bar is equal to mu, and then the standard deviation of sampling distribution is sigma over square root n. Okay, so that's the central limit. This is really important. Okay, so keep in mind the central limit theorem is not talking about uh, the uh, the sample mean, or I mean just statistic. Okay, a statistic of single sample. Okay, keep in mind this is not individual sample. No. Okay, central limit theorem is talking about the statistic of sampling distribution. Okay, so it means that central limit theorems is talking about the statistic of multiple statistic of multiple samples. Okay, so in here mu x bar represent the mean of sample mean. Okay, so from the for example 100 or 1000 and 10,000 samples, we calculate the sample mean, and then we figure out then the mean of those sample mean is denoted by mu sub x bar, that is equal to mu, and then standard deviation of those sample means denoted by sigma x bar is equal to sigma over square root n if this population is normally distributed. And then look at the second statement. If the no, if the population is not normally distributed, but sample size is greater than 30, okay, then simple mean x bar is approximately normally distributed with a mean here. The mean is doesn't mean that the sample mean. Okay, that mean is a mean of sample means. So it means that that's the mean of sampling distribution. So mu x bar is equal to mu, and then sigma x bar is sigma over square n. So let's see example. An elevator has a posted capacity of 16 passengers, or 2,500 pounds. This means with 16 people on board, the average passenger could weigh approximately 156 pounds. So the now man's weight are normally distributed with mean 182.9 pounds. You see that here, and then standard deviation 40.8. That's the what? This one from here we can figure out the population mean and the population standard deviation, right? And then also population normally distributed. So mu is a 182.5, and the sigma is a 40.8. Now, is the elevator safe for 16 men to ride? Okay, so you see, question A. Let's figure out the answer for the question by solving those two sub-questions. Find the probability that one randomly selected man weighed more than 156 pounds. So, all right, so in this question A is um, find the probability that one randomly selected man weighed It's more than 156 pounds. So that problem is not. Look at this. Is that problems? Uh, can we solve? Do we have to solve the problem using central limit theorems? The answer is no. Okay. So then what? What kind of problem? What the problem or what circumstance we have to use central limit theorems? Okay. How can you figure out whether or not we have to use the central limit theorems? So when you look at the question is the mentioned that the individual sample, then you don't have to use central limit theorems. Okay, but the problems mentioned the mention about the multiple the the samples statistic of multiple samples, then you gotta use central limit theorems. So here question is this: to solve the before solving the question A, so let's figure out the problem first. So now the problem says the population is normally distributed. Then the graph of the probability distribution of the population, so means weight, is should be like this pear shape. Okay, and the problem says that uh the the main the mean of man's weight is 182.9 pound, right? And then standard deviation is the 40.8. Okay, so now then the here, so and then let's see question 8. Find the probability that p, okay, so it equals x is equal to more than, greater than, or equals 156. Okay, let's say this x represent the man's weight. Okay, okay, so find the probability that a man's weight is greater than or equals 156. 156 is in the in the graph, maybe right there, 156. Okay, so then since x is greater than or equals 0, then we have to find out the area of the shaded region from 156 to the infinity, right? Okay, how can I find this? We gotta use a normal PDF in the calculator. Okay, so now then keep in mind is in the, by the way, it's still, if you still don't understand what um does this graph mean, okay, so this is the probability distribution of the in this example, this is a probability distribution of the man's weight. Okay, so the for example, you see in the US, we let's say we can we could collect all the man's weight, the data. Okay, the population. Okay, right. See, so we got the list of the all the US citizens man's weight. Okay, so now then we just the what let's see, we just plot the graph of this one. We got this one. Okay, so we figure out the what the frequency of each the data. We got this. Okay, right. But look at this. Keep in mind this: the weight or time, height are not discrete number. It's continuous number, right? That's what we're gonna get the this curved graph, not the not a histogram. Okay, and then and then you see here the bell shape. So if the probability, there are several three way to represent this probability distribution, right? The first one is a graph. Second one is the table, and the third one is a formula, right? So normally we have, I mean, we haven't seen the table probability distribution table when we deal with the we need to deal with discrete random variable, right? So now, but anyway, so in this case, we definitely the weight is continuous random variable, so we get that graph. Okay, so now then, what's the vertical axis represent? This is a probability. Okay, probability. So probability that our main weight is 156 is what? Right there. That's probability. Okay. So then what about the probability that x is greater than or equals 156? It means that we're going to find out that height not only at x is 156, but also every single real number starting from 156. Okay, that means what? The area under the curve from 156 to infinity. Okay, sorry, but we gotta use normal CDF in the calculator. Okay, so then the calculator, so we go to the distribution. Okay, you see normal CDF right there. Okay, lower is 156, and then upper is infinity. But I told you, a calculator doesn't recognize the infinity. Okay, even there's no the key in the infinity, right? So we put the 99999. Okay, we can put more 9. Okay, that's fine. And then mu is a 182.9. So 182.9, and then mu sigma is a 40.8. Okay, we paste, and then we got enter. We got the 0.75 at 0.745. Okay, so that is approximately 0.745. Okay, all right. So now let's see the question B. Question B. See. Question B. Find the probability that a random sample of 16 men has a mean weight. Is it a mean weight? Greater than 156 pound. Okay. So it means that what the the sample mean, okay, the mean that sample mean, okay, is greater than 156 pound. Then we have to figure out the sampling distribution. It means that distribution of sample means. It means that multiple sample means are involved, right, in this problem. Then we got to use central limit theorems. So in equation B here, let me. This is, by the way, this is a probability distribution of population. Okay. Okay. So what's the population in this problem? I told you this is population means that the set of, I mean, collection of all of the mains weight data. Okay. Now, so here, this is x right here. Okay. So we drew the sampling distribution. Okay. How can you guarantee that the sampling distribution of, see, give me right uh the sampling distribution first. Okay. Sampling distribution of the x bar, sample mean. The x bar means the sample mean. Okay. So now this is the x bar right here. Okay. This should be bell shape. Okay. This should be the bell shape like this. Now then and then central limit theorem says that if population normal distributed, yes, see that in this example problem, population is normal distributed, right? And then for any sample size n, okay, in this case n is just 16, right? 16. And then the sample mean x bar is normal distributed. You see? So by the central limit theorems, we can say that sampling distribution of x bar is normal distributed, and then mean of sampling distribution of x bar going to be denoted by mu x bar is equal to mu, which is 182.9. And the standard deviation, sigma x bar, is sigma over square root of n. So here the sigma is a 40.8. Sigma is a population standard deviation, which is this. Divided by n is 16, right? So we got the 40.8 over 4. Okay, so where is a 156 pound? Right there. Okay, you may say that, okay, those graph looks, I mean, are almost same. No, actually the look at this. That standard deviation here in the population, probability distribution of population, is sigma is a 40.8. But here, the standard deviation is 40.8 divided by 4. So he in this graph has a much what less standard deviation than this one. Okay, it means that what? The most of data is around the mu x bar. Okay, I mean, more data than this in here, more data in here around the mu x bar, I mean mean, than this. So graph must be actually not like this, but give me a second. So actually graph must be like that. It should be like this. Okay, still bell shape. It's bell shape, so it's normal distributed. Okay. All right. So how can I find out the here probability that what the x bar? This is a question. Okay, x bar is greater than wait, greater than, okay. So or greater than or equal, it doesn't matter. Okay, greater than 156. Okay. So the then we're gonna use the normal CDF. Okay. So because we gotta find out the area from under the graph of the sampling distribution of mean x bar from 1 to 56, I guess. Then we gotta use the numerous CDF. So we go to the distribution, and then you see that numerous CDF right there. Okay. So lower is 1 to 56, upper 999, mu 182.9, exactly same as the before, but sigma is not this. 40.8 divided by, let's see, 4. So we got the 0.995 in. So this is approximately 0.99 and then 6. Okay, I just round up. All right, so back to the problems. Look at the question. We didn't figure out the question of the example, right? Is the elevator safe for 16 men to ride? No. Why? Because it turns out that what? The mean of sample mean, okay, I mean mean of sample, I mean the probability that, you see that here in the second question, the probability that random sample of 16 men has a mean weight greater than 156 pounds is 0.996, almost 1, right? So it's you know so it's very, the likely, you know we can say that the 16 people, okay, the I know, so 16 people, the definitely we gotta assume that actually 16 men, right? 16 the man's the mean weight is greater than 156 pounds. So it's likely to be greater than, I mean, their weights greater than 2,100 pounds. So the elevator safe for 16 men to ride? No, based on the that statistic. Okay, that's the answer for the question. So cans of regular Coke contain a mean of 12 ounces as labeled with a standard deviation of 0.11 ounces. Find the probability that a random sample of 36 cans will have a mean of 12.10 ounces or greater. So now the just take a look at the question. Find the probability that a random sample of 36 cans will have a mean. You guys see the here mean of 12 points. So this problem is about the mean of sample mean. I mean the mean of sampling distribution of X bar, right? So then we gotta use central limit theorems. So the since you see the sample size is 36, which is greater than 30. So even though the problem doesn't mention that the population is normally distributed, but since the sample size is greater than 30, we can use the central limit theorems. So here the mean of the see uh, here population mean is 12 ounces, and then standard deviation is sigma is 11, right? Okay, so now then we use a normal CDF. So example, so population uh, mean is the 12, and then population standard deviation, let me just STD, stand for standard deviation, is the 0.11, right? Then the the sample, say that the mean of sampling distribution, uh, sample mean is going to be 12, and then the standard deviation, sampling distribution, the standard deviation sampling distribution of sample mean is the sigma, which is 0.11, divided by square root of 36, which is 6, right? Because n is 36. So okay. So now using this information, we're gonna enter this information into the calculator and, using synthetic intrinsic function normal CDF. Okay, normal CDF. Okay. Question is this. By the way, what's the question? Find the probability that x bar, okay, sample mean is, you see that will have a mean of 12.10 ounces or greater. So okay, greater than or equals 12.10. Okay. To solve this, to find the probability that sample mean is greater than or equals 12.10, we use the normal CDF in calculator. The lower going to be 12.10, upper is 99999. Okay, and then the mean going to be the 12, and then standard deviation is a 0.11/6. Okay, so let's figure out the answer then. So in the calculator, so we go to the distribution. There's the normal CDF. So lower going to be 12.10, upper 9999, and the mu is the 12, and then sigma is the 0.11 divided by 6. Okay, paste. So we got 2.46. Is it 10 to the negative 8? Negative 8 means a 10 to the negative 8. So this is really small number, right? Okay. So it means that since this is less than 5%, right? So this is significantly low. Okay. So it means that what? The probability, what? Does the mean, the simple mean, the mean of the sample of 36 cans, um, really, really it'd be really greater than 12.10. Okay, so in the graph here, so we can say this is x bar. It's a graph like this, and then here mu x bar is the equal to mu, which is 12, right? And the sigma x bar is the sigma over square root of n, which is the 0.11 divided by square root 36, which is a 0.11/36, 6, right? Okay, and then with the 12.10, 12.10 is maybe right there. Okay, 12.10. Okay, and then we just figure out the area on the graph. That's the probability. Is the probability that x bar is greater than or equals 12.10. That was 2.46 times 10 to the negative 8. Okay, this is almost 0, right? Almost 0. So graph must be more not like this, more not like that flat. Okay, so maybe graph like this. Okay, so let's see next problem. Okay, manhole covers must be a minimum of 22 inches in diameter. The man's shoulder breadths are normally distributed with a mean of 18.2 inches and a standard deviation of 1 inches. So what, question A, what percentage of men will fit in a manhole. It means that we have to find out. I mean, the question asks us to figure out the probability that men will fit in a manhole. It means that men's shoulder, the breast, uh, are less than or equals 12 2 inches, right? Okay. So because the men's shoulder breadth are less than or equal to 12 2 inches, then what the man will fit in a manhole, right? So give me a second. So here we need to figure out, and this is a question. Here we need to figure out probability that. Okay. So let's say the random variable x represent the man's shoulder breadth. Okay. This is less than or equals 22 inches. Okay. By the way, so the problem gives us the population mean and standard deviation, right? This is x. Okay. Normal distributed. Because the problem says the man's shoulder breadths are normally distributed. Okay, so the mu is 18.2 inches, and then sigma is 1 inches, right? Okay, so now the to find out this one, x 22 inches, maybe 22 right here. Okay, we need to figure out the area under the curve under the probability distribution of man's shoulder breadth. Okay, from negative infinity to 22 using the calculator. I'm going to use normal CDF. So go to the distribution. Okay, so now we use normal CDF. Is a 9 negative, right? Negative 99999. Upper gonna be 22. The mu is 18.2, and the sigma is 1. So we're gonna get 0.999. So it means that what percentage is it? So it's 100%, right? So now then you see next one. See, question B is this: if 36 men are randomly selected, what is the probability that their mean shoulder breadth is less than 18.5 inches? Could the city save money and make manholes 18.5 inches in diameter? You see, so right there. Okay. So now you see that here. Then is look at the question A. So the 100% means uh you know the man will fit in a manhole. So I think the maybe we have to reduce the diameter of the manhole, right? So in the question B, so 36 men are randomly selected. Okay. And then what is the probability that their mean shoulder breadth is less than, you see that? It means the sample mean is less than 18.5 inches. Okay. So they are not asking us to find the probability that a single value, I mean random variable shoulder breadth, I mean, is less than 18.5 inches. No. Mean of shoulder breadth. Okay. It means a sample mean. Okay. Less than 18.5 inches. Okay, so let's figure out this. Since we can use I mean, definitely we can use central limit theorems, because you see the problem says that what population is normally distributed, and moreover what the sample size is greater than 30, right? Okay, so now in question B, what are you gonna do? So we need to figure out what mu x bar and then sigma x bar, right? So mu x bar is equal to mu, which is a 18.2 inches, right? And then sigma x bar going to be sigma over square root of n, which is 1 over square root of 36, which is 1 over 6. Okay, so definitely graph of this. This is the graph of sampling distribution of x bar. Okay, so mean shoulder breadth. X bar means mean shoulder breadth. Okay, so this is x bar right here, and then mu x bar, 18.2 inches. Okay, and then sigma x bar is 1/6. Okay. So now we need to figure out probability that their mean short of breath is less than 18.5. 18.5 maybe right there. 18.5. Okay. Inches. So we figure out area probability that the mean short of breath is less than 18.5. It means that we're gonna find the area from 19 infinity to 18.5 under the graph of the sampling distribution of x bar. So now let's see. Okay, so he calculator. So we go to the distribution and then we use a normal CDF. Then -99 to 18.5. Okay, mu is 18.2. Sigma is 1/6. So we got 0.964. It's a 0.964. Okay, so the probability that in a V, okay, probability that x bar is less than 18.5 is approximately 0.964. I mean 964%. Okay, so most of men's I mean most of samples, their the mean, again, mean value, I mean their mean is the less than 18.5. So now just look at the question. Could a city save money and make a manhole 18.5 inch in diameter? Yes. Yes, because the mean of sample, I mean most of samples, their what um let me see, the sample there the 96.4% of samples, their mean is less than 18.5 inches. Moreover, look at the question A. 100% of men, their shoulder breadth is what, less than 22 inches. So they gotta reduce the diameter of manhole for safety, right? Okay. So I solved the problems about the central limit theorems. The central limit theorem is really important. This is kind of fundamental theorems in statistics. So you gotta understand completely. Okay. So I'll stop here, and then next time I'm gonna cover the 6.5 briefly.